Okay.
Okay, we are ready. Let's go.
All right. So let me start sharing my screen. Hopefully everybody can see the presentation now. And let's begin.
Sorry, Marcos. Sorry,
yes.
Sorry again for interrupting you. A last notice for all the participants: please write your real name in your profile in your panel, because it is critical to have the participant list from each webinar. So if you have connect with maybe your smartphone and you see instead of your name an iPhone i4 or a Xiaomi Redmi 1, the name of your mobile phone, please change your name. If you go in the three dots on your panel, you will find the ability, the setting rename, and change, write your real name. Okay, thank you. Okay, Marco.
Okay, Thano, can you see my screen, my presentation? Okay. So this is the second webinar, guys, of the series provided by Enter. Today we're going to go through the 3D printing hardware. So basically we're going to go through the most important parts inside an FDM 3D printer, the parts that make a 3D printer work. After that, we're going to follow the process of actually creating a 3D printing part from the start to the end. And I will show you some methods in order to give this part a more professional look for those of you who want to create a startup, let's say, from a 3D printed model, prototype. If you remember from the previous webinar, we talked about rapid prototyping. So this is a way to create something and give it a more professional, smooth look that will catch the eye of the customer. So now let's go through the content real fast. Give me a minute. Okay. So let's go through the content. First, we're going to show you the FDM printer that we're going to discuss about. Spoiler alert, it's called TiVo Tornado. Then we're going to talk about the frame, the heat bed, the hot end, the stepper motors that move our printer, the extruder, the control. Oh, this is a mistake. So the control box is written twice. So we're going to talk about the extruder, the control box, how to print the model. As we said, we're going to go through all the steps of how the actual printing process goes, and the post-processing in order to smoothen our model. So first, we're going to go through the printer hardware. And our printer, as I said, is called TiVo Tornado. This is the printer we're going to talk about today. The Tornado is an affordable large volume 3D printer made by TiVo. TiVo is a manufacturer based in China. The Tornado comes mostly assembled, requiring minimum assembly by the user. So basically, you have to fix some of the parts on the printer when you buy it. It's not already assembled. It has aluminum frames that provide this sturdy look that you can see. And what TiVo advertises is the smooth and precise 3D printing thanks to the Vslot linear guiding system. Now, more specifically, the printer can print with a maximum size of 300 by 300 by 400 millimeters. Like most of the entry printers out there, its extruder is full metal, and it's called E3D Titan. The extruder type is Bowden. Keep that in mind. Bowden means that the extruder is separated in a hot end and a cold end through a tube. We're going to talk and discuss about it in a moment. It can also print, instead of just standard PLA, ABS, and PETG filaments, it can also print wood filaments, PVA, flexible filaments. Its nozzle size is the standard one, which is 1.75 millimeters. It can print one color at a time, and its position accuracy on the z-axis is 0.0004 millimeters, and at the x and y-axis, it's 0.012 millimeters. Now, at this point, I would like to mention that the position accuracy of the printer is one of the most important factors that define the cost of the printer. For example, a Tivo Tornado costs roughly, let's say, 200 to 300 euros. If the position accuracy is doubled, the Tornado would probably cost more than 1,000 euros, just because of the accuracy of the hot end. Because the accuracy is given by the steppers, and in order to have better accuracy, you have to buy better steppers, and better steppers are costly. So now let's go through all the parts of the Tivo Tornado. Let's talk about the frame. In the pictures, you can see that the frame of Tornado is highlighted by yellow lines. The frame of the 3D printer is a very important part. It may look simple, but the design can actually be quite complex. This is due to the many different design possibilities. The importance of the frame is attributing to the following three factors. It supports all the mechanical and electronical components that carry out the actual printing work. You can actually see this here. All those parts are actually on the frame of the printer. It determines the build volume of the 3D printer. So the bigger the frame, the bigger your model. And it gives the printer its robust look as well as its aesthetic appearance. When choosing a 3D printer frame, one has to consider ease of assembly, strength, durability, as well as the application in terms of desired build volume, as we said. Aesthetics may be a great consideration to designers and businesses who may want their printer to look good and presentable to the public. However, it may not be an issue to printers that we use for experimentation or basic 3D printing. Now, if you search on the internet for FDM printers, you may notice that most of them have aluminum and steel profiles, which look like those ones here on the left. One question, Thanos, can you see my mouse that I move here?
Yes.
Or no?
Yes.
Okay,
yes.
just I want to know so I can show you things. Okay.
Yes, it's okay.
Okay, so those profiles here are the standard profiles for most of the printers. As you can see on the right, most of them, even this one has aluminum frame, which is covered by plastic or more aluminum. The reason is that these profiles are fairly cheap to find, but they are great in terms of durability and vibration resistance. This is why most manufacturers decide to use this type of aluminum or steel profiles in order to create the frame of their 3D printer. Now, moving on to the heated bed, early 3D printers didn't have heated beds. To encourage prints to stick to the cold surfaces, materials such as painter's tape were used to improve adhesion. It didn't take long, however, to realize that most materials bound better to a warm print surface, and that this also brought several other important advantages. FDM printers extrude molten plastic at a temperature high enough to allow it to flow, but low enough for it to cool and re-solidify in a predictable way. However, if cooling happens too quickly or the extruded filament reaches too low of a temperature, it contracts too much. Internal stretches build up and adhesion and warping issues start to occur, as you can see in the middle, especially at the interface with the printing surface. That's why the heated print bed should be on a high temperature while printing. Now let's have an inner look onto the components that the heated bed is made of. As you can see in the first picture, the surface of the heated bed stands on a steel base. In the middle picture, you can see the main components of the heated bed, which is the hidden surface. That's why if you was closer, if you can see closer, it says do not touch, because it may cause you burns. And on the last picture, you can see the way that the heat is transferred to the surface. So basically what happens here is that those parts that look like batteries with a yellow color, these are called heaters. As you can see, we supply those heaters with electricity through those cables. And since they are attached to the surface, they transfer the heat to that surface. Keep in mind that this step takes a little bit of time, let's say 2 minutes, in order to bring the surface to the desired temperature. Moving on to the next slide, we can see some types of covers for our surfaces. The most common one is the glass cover, which is simply a glass surface added on the top of the heated surface, so that we can extract whenever we want to. Another type of cover here is the mirror cover, which is similar to the glass cover. And last but not least, the magnetic cover, which is a plastic sheet which is resistant to heat, and it sticks on top of the head of the heat bed surface without the need of clamps or anything else. The way that it helps it stick is a magnetic force. This type of cover is great for beginners since the top surface is not smooth, in order to help the first layer in order to help the first layer of the model stick on the bed, so that we don't have adhesion problems. Now, since we already talked about the adhesion problems, let's see the adhesion solutions. As I said, not many adhesion problems occur when you have this plastic magnetic surface. But what about the glass surfaces? The most standard product most people use in order for the model to stick on top of the bed is a classic glue. As you can see on the first picture, this method is very easy. The glue can be found everywhere, and it actually works great, guys. Another way to help your model stick on top of the bed is the use of duct tape, which, as I said before, was the way to go for the early 3D printers that didn't have adhesion beds. And my personal favorite that I have at my home for my printer is the hairspray, because it is the fastest one. And also there are special sprays in the market, like the one shown in the picture. I think it's called Dymafit, I'm not sure. That they are used for these reasons, which don't stick anywhere but the bed, and they actually do a great job. Okay, as we've already said, in order for the 3D printer to print a 3D model, we need to actuate three axes: the X, Y, and Z axis. The X and Z axis are actuated on top of the bed where the hot end is. But the third one, the Y axis, is actuated on the bottom of the bed. Let me show you on the video in order for you to understand. So this axis is actuated through a stepper motor, but we disabled the stepper motor and we move it by hand. Moving on to the hot end, that's where the whole work is done. Now, the hot end, or in other words, the heated nozzle, is one of the most important components of a 3D printer, as it heats the filament and pushes it through the attached nozzle. The filament melts and it then becomes again solid. Heat ends are actually durable conductive metal assembly consisting of a few elements, which we will see in the next slide. The hot end is a critical component of a 3D printer, and issues in the area can have significant effects on the print. The most common issue is a hot end in a hot end is a clog, which can lead to incorrect extrusion or no extrusion at all. And the common cause of hot end clogs is heat creep, where heat climbs beyond the melt zone of a hot end and material melts too early, blocking the filament path. While certain external factors can prevent heat creep, the quality of the hot end plays a big role. The better the hot end is at containing heat and establishing a coastal melt zone, the less likely we will have a clog. Now, before deeply analyzing the main aspects of a hot end, some aspects of plastic filaments need to be taken into account. First of all, plastic is a combination of a polymer and additives. A polymer can be described as a material made of long and repeating chains and molecules. All these chains can modify their viscous behavior depending on the material. At this point, in most of the polymers, there are two critical temperatures: glass transition temperature and melting temperature. Glass transition temperature is when a polymer is in a semi-crystalline state and its chains have no mobility. Beyond the glass transition temperature, it turns to a rubbery state, expanding itself, and the chains gain some mobility. So think about the plastic that starts becoming rubber. It's more squishy, let's say, after the glass temperature. And then we move on to the melting temperature, while it heats more and more and more, which is another transition point where the polymer turns from solid to liquid. So it can be extruded easily as the chain breaks. So what happens here, that you can see on the picture, the filament is fed through the nozzle while it is at room temperature. It starts heating up while going through the PTFE tube, but stays in the glass transition temperature until it hits the melt zone, where it becomes liquid and it is ready to be extruded. After the plastic is extruded through the nozzle here, it starts to cool and returns to its original temperature, which is the room temperature. Keep in mind that most hot ends have coolers somewhere here after the nozzle attached to them in order to help the plastic cool faster after it leaves the nozzle. Now let's see some components on the photos here. First of all, there is the nozzle here, which is the part where melted filament comes out of the hot end. The size of the nozzle defines the resolution of the XY plane and therefore the print quality. That's why we said that the better the nozzle, the better the quality. Then there's the heaters right here. We joined the nozzle to the heat break, as you saw in the previous picture, and it holds the heater cartridge and the thermistor. The heater cartridge is the component which heats up the hot end, and the thermistor is the part that senses the temperature of the heat block. Now these two are inside the heater block somewhere right here, so it wasn't easy to show you. They are very small, they're tiny, so basically there was nothing to actually show you. What a thermistor is actually, to say it in easier words, it's actually how can you say it? It's a way to measure the temperature of the hot end. And there's the heat sink right here, which cools down the cold part of the hot end using a fan. And as you can see, it is made of aluminum to easily separate the heat through the fins. So what happens here is the same that happens to most cooling fans, for example, on your PC. You may, if you open it, if you open the case, you may see on the fans these little aluminum designs like this. So this is an easier way to transfer heat to the room in order for your printer to keep the right temperature. So, as we said, the 3D printer moves in the X, Y, and Z axis. And two of those axes, the X and Y, are actuated through the move of the hot end. So we saw in the previous video the Y axis. Now we will see the X and Z axis move. This is the X axis. Close the volume. And as you can see, you can also move the Z axis through a metal part that you can rotate. This is actually called rack and pinion for the mechanical engineers out there. And yeah, that's how it works. It rotates, the stepper rotates this part right here and goes up and down. What is that? Okay. Now, how are three things moving on a 3D printer? There's at least 4 motors on a standard FDM 3D printer. So 3 motors are one for each axis, So, okay, what happens? Miss Vasilena, could we mute her? Okay, perfect. Okay, let me restart. So there's three axes, one for each separate axis, one for the Y, one for the Z, and one for the X axis. And then there is an extra motor for the extrusion of the filament. So basically, what the fourth motor does, oh, how did I do that? Okay. So basically what the fourth motor does is push the filament inside the hot end. Now, how do they stop? Every motor has a stop switch at the end of their movement. Now, when it touches the switch, it stops moving. This way, if, for example, we don't program the 3D printer correctly, the motors will not spoil because they will always stop when they meet the switches. Apart from the motors, in order for the hot end to move, we need belts, which will connect the motors with the hot end, and guides in which the hot end of the whole structure can move on. Now, the guides are basically the frames on this case. These are the guides. As you may see, these little parts move the hot end from here to here, and they are called belts. And the steppers are, one is here, the other one is down here, and the extrusion is done right here. Now, let me show you. Now, the hot end moves down. And for example, if we failed to program our printer right, what happens is that it goes down and down and down, and it meets the switch, and it stops. So that's how we save our printer from total destruction, let's say. Okay. Now these are the things basically that I showed you: the stepper motors, the rack and pinion on the Z-axis. This is the belt here that moves our part right or left, or here it moves our Y-axis on front or back. The stepper motor is here again. And also we have those rollers that help the hot end move right and left. And yeah, hopefully you understood how it works. Now, anybody that has questions regarding how a 3D printer works can keep that until the middle of the class that we will stop, and you can do the question there. Now, let's talk about the extruder. So basically here we're going to talk about how this magic thing creates 3D models. Now, this is extruder is basically probably the most important part on the 3D printer. The filament extruder on an FDM printer is the part that extrudes a plastic filament in a liquid form, as I showed you before, and it deposits it on a printing platform by adding successive layers. The printed head is made of many distinct parts, including a motor to drive the plastic filament and a nozzle to extrude the plastic. Some 3D printers are now equipped with true extruders. This enables them in particular to print two materials simultaneously in order to obtain 3D prints with two colors. The presence of true extruders also allows support material to be extruded, which can be removed afterwards using a solvent. Now, most people, when they refer to the extruder, they are talking about the cold end, this part. The cold end is a part that utilizes the rotation of a gear with the use of a motor in order to push the filament here inside the tube. And the tube goes, the filament goes through the tube to the hot end, as you can see on the picture, and then it melts. But the truth is that the extruder module includes both the cold end and the hot end. So most people think the extruder is this part, but basically the extruder is all of this part. Now, right now in front of you, you can see two types of extruders. The right one, this one, is the Bowden extruder. Now, in the extrusion system, what happens here is that the cold end and the hot end are positioned separately. If you remember, that's how the tornado works. And they connect through a tube. Inside this tube, the filament is fed from the cold end to the hot end. On the left side, you can see a direct extrusion system. And the only difference here is that the hot end and the cold end are basically positioned together. In this case, there is no tube. The filament is fed to the cold end, and it directly moves to the hot end in order to print. Now let's do a small comparison between those two. The Bowden extrusion system has cleaner movement, meaning that since the cold end is not attached to the hot end, there is no vibrations from the motors of the cold end, which could end up to a bad print. Also, since we can place the cold end anywhere on the printer, we have the ability to create printers with larger build volume. But on the disadvantages, we need a more powerful motor in order to overpass the friction inside the tube. We have slower response times between the cold end and the hot end, and sometimes this leads to material complications and print failures. On the other side, we have the direct extrusion system, which is more reliable in terms of extrusion and therefore in terms of retraction also. We need a less powerful motor since the systems connect together and it works with a wider range of filaments with ease. And on the cons, as we said, since the system connect, we have vibrations from the motor, and also it's harder to do maintenance since everything is together and it's hard to understand where the problem is sometimes. Now here you can see how the extruder functions. This is a Bowden system, by the way. So this is basically how our TIVO tornado works. The filament is fed at the beginning inside the cold end. The stepper motor rotates here through a small gear, which rotates a bigger gear. And with the help of this bearing right here, it pushes the filament inside the Teflon tube. And when the filament reaches the hot end, it starts to heat up and melt and extrude it from the system as liquid. Now let me show you this video. So the part that you see here is the cold end. As you can see, the stepper motor feeds the filament through the tube, and the hot end should be somewhere right here and print, melt the filament and print. So this part here is this one. As you saw, it actually rotates. There is a bearing here, and it pushes the filament step by step by step. So it always calculates the amount of filament needed and then pushes it through. All right. Now, the last thing, no, this is not the last thing. This is the extrusion problems. So let's talk about the extrusion problems a little bit. Keep in mind that the big gear we just saw before should be positioned perfectly before every print. Because of the gear, if it's too loose, then the extruder will not be able to feed the filament to the hot end. On the other hand, if it's too tight, it may spoil the form of the filament, like the one you see here. So it may spoil the form of the filament, and even worse, it can actually break it. And all these things will lead, of course, to under extrusion problems, failed prints, and your prints will probably look like this at the end. Okay, and now we're moving into the last thing, the control box. I think I have some videos on that one. No, after that one, after the control box, there's some videos on how to print. Okay, now the control box, or in other words, the controller board, is responsible for all the electronic functioning of a 3D printer. Without it, the printer wouldn't be able to do much more than turn certain components on and off at the manual flick of a switch. So the controller boards handle all the logic behind the 3D printer, such as parsing G-code files, regulating temperature, and most importantly, of course, controlling motion. The latter is particularly important if we're talking about FDM or stepper motors. So, in simple words, the control box is basically the brains of our printer. From here, we can do anything manually, like, for example, move the axis through the motor, as you saw before, or heat up the hot end, or we can ask the printer to print something. If you see a problem, we can stop the printing process and restart it or resume it just by using our control box. Now, what do we need to do so we can start printing? Let's see the steps we need to follow. So this is a printer printing. There is not much to talk about this because when you reach this state, you must probably have done everything you needed to do. So we will go through the steps before this one. Okay. First of all, we need to feed the printer with some filament. Let's see the video. So as we said, we use the brains of the printer, which is the control box. This is a control box of the TiVo. So same as a computer that runs on iOS or Windows, printers have their own program that they work on. This is called Marlin. And now what we do is we preheat the hot end here. So now the hot end starts to raise in temperature. Preheat PLA. So first of all, we heat the hot end. As you can see, it starts heating, and also simultaneously, we preheat the print bed. So
Marco,
the print bed, yes.
Can you give us some recommended temperature for PLA and ABS, and in general some typical filaments?
Yes, so the PLA is the filament, the plastic filament that uses, let's say, the lowest temperatures. It works, it melts after 200 Celsius, and it's ready to be melted. The print bed, the heated bed, in most cases, even if it's PLA or ABS, we keep it on 60 to 80 degrees. So we keep our print warm, as we said on the start. And if you work with PETG or ABS, then you will probably need to heat your nozzle on higher temperatures. I'm pretty sure that PETG needs a very high temperature, I think more than 230 Celsius. And after this, I think that it's not actually right for me to tell you the printing temperatures of other filaments, like for example wood filament or metal filaments, because each filament has its own temperature that we have to print on. So yeah, basically,
Thank you.
every time you buy a spool of filament, you have to check out what the manufacturer suggests, and just follow the manufacturer. That's the best practice, in my opinion. So right now, as you can see, we reached the temperature, so we fed the filament. Hopefully it won't lag. Tell me you didn't lag. Okay, let me begin. As you can see, we feed the filament through the coldent here. This is the coldent. We feed it through the bearing with our hands, and when it reaches the hot end, since it's already on, let's say, more than 200 Celsius here, we push it a little bit so it can go through. And this is when you see this little plastic part here, you know you are ready to start printing. Now we cut this part, and the nozzle is ready to start printing. The second most important thing to do is leveling the bed. So basically we start with the same way. We open the control box, and now what most, there are a lot of practices in order to level your bed. First of all, again, we have to preheat, because as you may know, different temperatures create different sizes on the nozzle or on the heated bed. So you should always have it heated. And when it's ready, we home the Z axis. So we go, let's say, on 0.000 of the Z axis. And when it reaches this point, we take a paper, a classic sheet of paper, and try to see if it can stick between the nozzle and the print bed. Now you will know that you leveled your bed if the paper goes through, but it's a little bit, let's say there is some friction between the paper and the nozzle. So when you feel okay by leveling on one corner, you have to repeat the process on all 4 corners. This way, as you can see on the bottom here, there is a rotation tool that you can adjust the height here, here, and here on those 2 back points. So this way you will be sure that you leveled your bed and you have the right orientation on every single corner. Now, for those of you that will buy a printer, most probably, if you don't want to buy a printer which will cost more than 500 or 600 euros, you will have a printer like this one that you will need to do this process manually. What I suggest is buying an additional add-on, let's say, a small component that actually can do the leveling automatically. Unfortunately, I haven't added it to the presentation. I should have, but in case you don't want to do this anymore, you can actually buy this component, add it to your printer, and do this process automatically. If you actually decide to invest some more money on the printer. But keep in mind that you can actually buy a printer that can actually do this automatically. There is no need to do this every time. One more important thing is that after your prints, if you don't harass, let's say, your 3D printer, and you remove your prints, let's say you let your heat bed cold, and then you remove your prints with care, there is no need to do this process again and again and again after you print. It most probably is ready for your next prints. Keep that in mind. Okay, so, oh, sorry. All right. Now, my personal favorite, the post-processing. Give me a minute. Now, let's see how a 3D printed model can become even better. Now, let me see the next one. Okay. Now, the first thing we always do after a print is removing the supports. The supports are these things right here. As the word indicates, the support is excess material used to support the model while printing. After the printing process, this material is not needed anymore. So what we need to do is carefully remove this material without ruining our model design. Now, there are tools to achieve that. Let me start playing the video here. My personal favorite is the rotary multi-tool that you can see used in here. Now, this tool is very simple to use. As you can see, the tool uses a motor to rotate. The only thing we need to do is attach the appropriate sanding attachments, and then you start the cleaning process. Now, this may take from 1 minute to several minutes, depending on the design of the model. As you can see, this is a simple design, so it will not take you so much time to smoothen the surfaces. Okay, so basically we're not going to show all you the video. This guy is basically doing the same thing over and over again. So let's move on. Okay. Of course, we can always use the traditional sanding methods. For the beginners out there and those who want to start 3D printing and creating beautiful prints, this is a great choice. Since the materials are very cheap, it is easy to find, and it is very easy to do. In any case, I would recommend watching a video in YouTube before starting the process, if you are a total beginner, because this way you will know which type of sandpaper to buy or how to do it without ruining your model, for example. Also, doing the sanding process manually, you can be more precise, meaning that sometimes even if you have a multi-tool, you may choose the manual method instead, so you will not do stupid mistakes. All right, now let's see the process of sanding, of how to sand a model the proper way by, let's say, a professional of the field.
Okay, first things first, do not forget to put your mask on, and then we are going to start sanding with a 120 grit sandpaper. Again, the coarser grit to really help knock those lines down. Now I've wrapped the sandpaper around a sponge. It helps me have a better hold of it because you're going to be doing a lot of sanding. So if we take a look here, we can see that the layer lines, they're still there. Again, not a lot in these helmets, really cool, but we still need to knock some more down. And again, I'm still using the 120, and you can see the more you work that, the more you'll get rid of these layer lines so that you're not going to have to do a lot more of the finer sanding later on. So you can see here the layer lines are almost gone, and you're going to want to do that across the whole helmet with that 120. And don't forget to get into the cracks and crevices. Again, this is why I like wrapping the sandpaper around a sponge. The sponge is soft, and it really lets you get into all those little spaces to smooth that stuff out. Now, here we've done the entire helmet, and it's hard to really see much of a difference, but if you look, you can see most of those layer lines are really knocked down. Now we're going to go with the 220. Again, as we move up, the sandpaper gets finer, and it's still doing its job, and it's just making a smoother and smoother helmet. Don't forget, as you're sanding, because you can sort of forget about this, it gets away from you, to do all the little bits of cracks and crevices, because you don't want those to stand out. Now we jump up to a 320. Again, a finer sandpaper, a finer finish on the helmet, and again, you're going to do the entire thing. Of course, you're still wearing your mask.
All right. Moving on to the next step, after the sanding process, we have to apply a filler material. The most commonly used material is a primer spray. Oh, wait a minute. Thanos, could you see the video well? Should I optimize it for video?
Now you don't play any video. I can see only.
No, yes, the previous one, the one we just saw.
Yes.
Was it fine, or should I optimize it?
It was okay.
Okay.
Don't worry.
I'm keeping it this way. Okay, so as I was saying, after the sanding process, we have to apply some filler material. The most commonly used material is the primer spray. This spray is also very cheap. I think it costs roughly 8 to 9 euros maximum, at least in Greece. I don't know in any other place. But I think since we have common prices in Europe, at least you will not find it more than 10 or 15 euros, and you can actually use it multiple times. So basically what you do here is spray the model where you fill the gaps that you need in order to create a smoother surface. Of course, after applying the filler, you can use some sandpaper and do some extra sanding if you feel like it. So let's see how to actually use this primer.
So even after all that sanding, there are still some layer lines. You can barely feel them with your nail, but they're there. So we're going to use some fillable sandable primer for that. Key thing is wash the print before you use this primer. Now, I like to put it in a bath of hot water for a little while. This stuff is thick, that's why it's sandable and fillable, and this way it breaks it up and makes for a great mix, and it'll coat it really well. Now, again, make sure you're not getting too close. Stand off, as the directions say, 8 to 10 inches, so you're not getting any runs. And just give this a really generous couple coats. Let it dry, maybe even get it another coat to fill in all those layer lines. Sandable fillable primer is magic. If you look at this thing, you can see here almost no lines now in this helmet. It's going to have a little bit of grit to it. You're going to have to do some sanding after this, but those major lines are gone.
So as you saw, those little points like this one here or this one, they are created by the primer because it touches the plastic and it solidifies. So basically what you can do here is that...
so even after all that...
Wait. Okay, so basically what you can do here is repeat the process until you feel that the model is smooth enough. Just be careful because this process, since you sand, then fill, then sand again, etc., it may hide some of the detail of the model, like those lines on the mask that you saw before. So let's see how you can repeat the process.
Now, if you remember, we did have some thicker grooves up on the top, and we're going to take care of those with some glazing compound. But before that, we need to sand this sandable fillable primer so it is smooth before we go ahead and put on our glazing compound. And again, while you're doing it, don't forget, work in these cracks. We don't want them to fill up with the primer and the things we're using. Now we're going to go ahead and give this thing a wash. I wash the print multiple times during the process to get a lot of that grit off. So here we go. Here's some of those thicker layer lines, and this is when we're going to use our glazing spot putty. And I like to use a piece of foam because it really helps me get into the cracks and crevices when I'm working. And you're just going to go ahead and, you don't want to sort of cake this stuff on, but you want to put enough in there to fill those lines to make sure that when you sand this, you don't see them. And some people go overboard sometimes with this glazing compound. I am guilty of it myself. You really only want to use it when you're taking care of these really thick lines and some of the minor lines throughout the helmet. At the same time, if you really want to get that smooth surface, you might go through the whole helmet like I'm going to do and find areas where you can still see some lines and take care of those. Because the last thing you want to do is get to the end and get ready to start putting paint on, or put the paint on and you start seeing some layer lines. Now, are there going to be a few layer lines here and there? Yes. I mean, we're going to do as best we can, but this is not going to be 100% perfect, but it is going to look pretty sharp. And don't be afraid to go ahead and get your fingers in there into all the little cracks and crevices to make sure it is taken care of. Here's an area I forget to do a lot of times, and it's the underside of the helmet. Go ahead and use your finger to fill in those little lines, because that is something that I forget, and then you can see that in the helmet, and nothing's worse than forgetting an area like that. Now, once the glazing compound is dry, you're going to go ahead and sand that. And this stuff makes a very, very fine dust. Make sure you're wearing a mask. If you can be doing it outside, even better. Now, once we've sanded it, I've given it another coat of the sandable fillable primer because you want to make sure you have that on there before you do your final paint. But as you can see, some of the details are getting gummed up with all this primer. So what we're going to do is we're going to use some of these rasps, some of these little tiny files. I got these at Harbor Freight. You can get them in Amazon or whatnot. You can find links below. And I'm going to go through the crack there into the detail to get rid of that and sand it smooth. Again, super easy to do, and it's a really, really important thing to make it look finished. Now, last thing we're going to do, yes, more sanding, believe it or not, we are going to do what's called a wet sand. So this is where you wet the helmet and or the sandpaper or both, and you work it with a very, very fine sandpaper. This is a 600 grit, and you are just going over all the details, and this takes care of all the sanding lines. Then I'm going to go ahead and wet it again and wash it down, and this is a 1200 grit. So this final wet sand takes care of any sanding lines and makes this thing glass smooth. Now, the key thing here is you're going to want to wash the helmet to get all this grime off with soap and water and let it air dry. In this way, it will be totally ready for paint.
All right, and then after this step, you actually paint it. And this is the final product. Looks beautiful, eh? Now, some last touches ended like this one that you can paint with brush after, of course, spraying the whole model. And this is the way, guys, to make something you pretty actually look professional. Let's say you invented a new gadget or a toy. So instead of showing this to an investor, which is something that just works, you may also show them something that looks great too. So as I said, this is how rapid prototyping works. And of course, there's more techniques to make your prints look better, like surface melting, which, as you probably know, PLA is not particularly heat resistant, which makes it great for outdoor, not so great for outdoor applications, but it does mean that you can harness the impact of heat on the plastic to finish your prints. So the most commonly used tool for this purpose is the heat gun. You just set it to its lowest heat settings. And the most consistent results are attained by placing the print on a turntable and spinning it slowly to evenly distribute the heat. This also helps prevent overmelting in specific areas for the overall better result, and it keeps your print, let's say, melted evenly. Now, another method is the epoxy resin coating, which works the same way like the primer does. However, it's a little more difficult to work with because you have to mix it before applying to your print. One thing epoxy, of course, performs significantly better than primer is filling the larger holes, because basically it's plastic or print artifacts that have been left behind by the printing process. Finally, we come to the chemicals. PLA can be smoothed with acetone in the way that ABS can, but there's still an option to achieve a similar finish. Now, Polymaker Polysmooth is a component like it's a machine like this one, and it is composed by PVB, which is a very similar material to PLA that can be chemically smoothed. However, it requires the use of the Polymaker polyser. This is a box, this one, that dispenses isopropyl alcohol, which reacts with the filament to smooth the top layers. So what happens inside here is the same thing that happens with surface melting when you use PLA, but instead of actually heating the parts, we add alcohol inside the machine, which will create this, let's say, melting of our part in order to smoothen it. So different ways for different materials. And this is where I stop my presentation and you start your questions. That's it. We're finished for today.
Thank you, Marco. Thank you for this very interesting presentation. So guys, do you have any question for Marco? What do you think about this presentation, about the hardware of the 3D printer? Do you find it too complicated? Do you have any question about a particular object, a part of the 3D printer?
Nothing, nobody. So hopefully everybody understood exactly how the extrusion systems of a 3D printer works.
Probably.
No question?
So, Marcos
question.
asked, you said before that it's better for us to find out the temperatures
Yes,
regarding
When-
the ABS or the PLA suggested by
Exactly.
the manufacturer. It's
Exactly.
a better procedure.
Mhm.
If we don't follow those instructions, what will be the result?
If you are lucky, there will be no problem because you will know that, for example, PLA works from 200 to 220 Celsius. So most probably you will have the correct temperature. Now, if you're not lucky, you may have, in the best case, you may have a print that doesn't have the print quality that you could actually achieve with a better temperature. So in some points or at some time you may see overheat, over extrusion or under extrusion, like as the one we showed. Let me show this. Let me reshare and show this. So hopefully everybody can understand what we're talking about here. No, I passed through it. Where is it? Where is it? There it is. Okay. So this one is called under extrusion. So you may even see this on your print because you had the clog. So the same thing that may happen when your extrusion is when the gear is too tight or too loose, as we said before, because it pushes a lot or it doesn't push as much. The same thing will occur if you have high or low temperature. Your basically your filament will not be pushed the way you want it to be pushed through the nozzle. And most probably you will see something like this, or in some cases you will see the one we call the spaghetti problem. So basically what you're going to see is let me show this. Okay, hopefully you will see this. Can you see that spaghetti problem?
Okay, Marco, take your time.
You will see something
find,
like this.
We can't see your screen.
Okay.
Because you are sharing only the presentation, probably.
Yes. Let me share.
Okay, until you make this setting, we have a question in the chat about where can you find this presentation. So as I told in the beginning of this webinar, in the next week, I think we will have prepared. We upload all the videos of the recorded videos of this webinar in our channel in YouTube, and we will then upload this material in the platform. So I believe that hopefully by the end of the next week, we will send to all the participants a mail with links about where can you find the videos of the webinar, the evaluation form, and the webinar tests. So, okay, probably by the end of the next week, you will have all this material. Okay, Marco?
Yes, so hopefully
Marcos,
now
yes,
you can
we
see.
We can see this. Yes, it's very understandable what spaghetti problem is.
Yes,
Okay.
exactly. So this is what you may see. In case you see something like that, I suggest you stop your prints and restart again, and then check your temperature better.
Okay.
So yeah.
Thank you very much, Marcus.
Okay, do you have any other question for Marco? Okay, we have a question, Katerina. You think this is not the right one? Let me check. What is the link that I sent you? This is the evaluation form for the second webinar. Let me check if it works.
Oh yes.
This
is the introduction.
This is the invitation. Sorry.
Mm.
Okay. Yes. Okay. Yes. Okay. Just give me a minute, and I will send you again the evaluation form. So I think this is the correct one. Let me check it again. Yes, okay. This is the one. I just upload the link in the chat. You can go there and please place your evaluation in order to have feedback. Yes, thank you. So if you don't have any other question, thank you again for joining this webinar and spending your afternoon with us. Please stay tuned. We will inform you with an email about the material when we will be uploaded in our platform, and you will have access to all this material. Next webinar is let me check the exact date.
I think it's 12.
12 of May.
Yeah, most probably.
Oh yes, in exact 2 weeks from now. Okay, so in about 2 weeks we will see you again.
Can I do a small introduction for the next one?
Yes, Marco.
Okay, so on the next webinar we will not see things on PowerPoint. Basically, what we're going to do is play with a slicing program. We're going to see how to prepare a 3D model, how to create supports so it stands on its own when you print it, We're going to talk about the temperatures even more this time. And generally, I would suggest those of you that want to start 3D printing and have no idea about how slicing works. First of all, since we're going to use the most commonly known program called Cura, Ultimaker Cura, you may download it from now because it's free, and because you can download it and install it in, let's say, 2 or 3 minutes. It's very easy. And play a little bit, add some models, just do some clicks, maybe go through the UI by your own for 5 or 10 minutes, just to understand what happens in this program. And hopefully you will be ready on the next webinar to follow through the steps that I'm going through. It's going to be very easy for you. And after the webinar, most probably you will be able to create the G-code file in order to input it to your printer. So yes, in my opinion, it's pretty important for those who don't know how slicing works, and for those who know how slicing works and want to see some extra, let's say, advanced settings for your printer. Yeah,
that's correct, Marco. Thank you for your input. Also, just upload in the chat the link for downloading the Cura slicer, and also recommendation for the next webinar. When Marcos will present the Cura, it will be very convenient for you if you can use 2 monitors. Watching Marco presenting you several settings in Cura in 1 monitor, maybe it could be a tablet, not necessary 2 PC screens, and you have your computer in the other side beside the tablet or your other screen, and testing these settings by yourselves. So that's all from us. Thank you for joining us again. Have a nice evening. Thank you very much.
Thank you all.
Hopefully we will see you in about 2 weeks.
Thank you, Thanos. Thank you, Marcos.
Thank you.
Bye. Have a nice evening.
Bye, everybody.
Thank you, everyone. Bye bye.
Ευχαριστούμε. Καλό βράδυ.
Καλό βράδυ.